I guess it's a super special presentation from us because I think this is the first time we've done this as a three. I'm Cong. I'm delighted to be presenting AI scientists towards fully automated open-ended scientific discovery together with Chris and Rob, who's also on the call. And we are the co-leads of this project. And this work was supervised by Jacob Forster, Jeff Clune, and David Ha. And please do feel free to interrupt and ask any questions if you like. Okay, awesome. So to first kind of set the scene around recent developments in machine learning, generative AI has kind of exploded in capabilities across many different modalities. So for example, in the image space from super early models like GANs and VAEs, we've now got extremely advanced diffusion and flow matching based models that now sort of accurately render scenes and also can even paint in text in images. On the other hand, for language, so this is sort of the epicenter of a lot of recent advancements in AI, we now have models that have begun to demonstrate strong problem solving and reasoning capabilities. And indeed, our work is largely powered by large frontier text models. Equally in video, we've now begun to see models that can coherently render long video scenes. We now kind of see the same moment coming for AI in science. So from earlier work in kind of developing strong predictive models, and indeed actually models that recently just won the Nobel Prize, for things like protein folding, we've seen like super good prediction models, aids to scientific writing, and now we believe that the time is ripe now for us to introduce the first piece of work that seeks to automate the entire scientific process, all the way from idea generation, visualization, writing to peer review, all in one open-ended system. And we like to highlight across all these different modalities, there's this collective trend of improvement over time, effort for democratization, open sourcing, and also validation from the community. Large language models have already been used for discovery in many domains. This typically goes via a sort of evolutionary style algorithm, where a foundation model continuously proposes interesting new designs conditioned on what's already been proposed. This kind of occurs in this loop that I'm sharing on this screen, where the foundation model keeps proposing new things, evaluates them, and then based on things like evaluation scores, it can kind of merge different concepts together or dig deeper into things that worked. There's been a large variety of applications of this, so this has been super useful for discovering things like novel robot morphologies, reward functions for RL environments. We're lucky here that this is work from led by Rob and Chris, doing kind of black box optimization with large language models and also discovering novel large language model preference losses for optimizing large language models themselves. So this has begun to also get super meta, where now we have this situation where large language models are now even proposing improvements to large language models themselves. And this is also kind of the theme of this work, ADAS, on the bottom left, where LLM agents are actually designing even better LLM agents. But science is much more than just the discovery of individual components. And the current human scientific community is a huge collaborative process. This ranges from human scientists identifying problems, creating hypotheses, brainstorming methods of inquiry, and conducting experiments. Then after this, scientists can then present their findings in a scientific manuscript, which then undergoes peer review cycles. And then after a lot of revision, this kind of thing is then finally published, and the knowledge is then disseminated. And then this kind of scientific process then starts all over again with our new understanding of the world. So the question we want to answer here is whether we can automate this entire scientific process with AI. And just like with the current human scientific community, can we have AI continuously propose novel ideas, carry them out with experiments, present their results, and evaluate their own findings? And then the grand vision here would be that these AI scientists can then accumulate their discovered knowledge and continue innovating endlessly, just like in the current human scientific community. So in this slide, we provide a sort of overview of the AI scientist. And this is the first fully automated pipeline, open-ended pipeline for research, which spans idea generation, experiment iteration, and paper write-up. From a sort of initial code base representing a toy run of popular ML baseline, the AI scientist can sort of seamlessly innovate and carry out its research idea in this manner. In the next few slides, we're going to kind of dig through each of these sections one by one. The first section of the AI scientist performs idea generation. So given some starter baseline code, for example, say training a simple transformer language model, or for example, a diffusion model on some two-dimensional data sets, the large language model continuously proposes novel ideas. So this very much happens in the same way as the sort of evolutionary framework that I described earlier, where you sort of add ideas to an archive and sort of iterate like this. And some key features of this, we can see the prompt on the screen. The agent is given all the code, a task description, examples of previous ideas, and is asked to come up with the next novel and impactful and creative idea for research. These ideas can then be scored. So we check versus semantic scholar, things like this, to make sure that the idea is novel. And then we can then archive it for later execution. So here's an idea that the AI scientist generates for two-dimensional diffusion. What we want to note here is that it'll propose a title for the paper, it'll propose experiments, and also numerical estimates for interestingness, feasibility, and novelty. And what I'd like to highlight in the experiments here is that this is much deeper than we kind of expected. We were at all kind of stages of development, we were kind of taken aback at how much of the process of scientific reasoning current AI systems could already do. So for example, here, not only does the AI scientist propose a novel idea and like modifications to the base diffusion model, it also proposes to collect, say, summary statistics evaluating how the new method works, and interesting ablations and analyses that I can later use in a paper. The second phase of the AI scientist then covers experiment implementation. So after it generates a bunch of ideas, we can then launch all these ideas in parallel. So from the initial template, we use state-of-the-art code assistants like Aider to propose changes that implement the generated idea. And these kind of state-of-the-art code assistants are really the powerhouse behind AI Scientist. And what these things do is, given the template and the idea, they continuously and iteratively make diffs to the template, run them and collect results, and then they can either correct errors in the Python code, or based on the results that they receive, they can replan and redesign results, their experiments. At the end of this kind of iterative process, the agent can then summarize all of its data in terms of plots and also visualizations. And this is kind of highlighting sort of this kind of plot kind of explains like why this is the right time for ideas like AI scientists to emerge. So, because we have to propose loads of changes to a code base, this becomes exponentially harder the weaker coding agents are. But recent advancements like Aider, for example, get something like 18% success rate on hard natural GitHub issues. And this is kind of the level of reliability that we need in order to begin to implement research ideas end to end. This is kind of our prompt. So we're given a number of max runs to implement things. And the broad structure here is that the agent plans out experiments, runs them all iteratively, and is allowed to replan. And all of these changes can then be automatically executed via these Python commands. One final slide before I pass over to Chris. So here's an example of a code diff that it generates for the highlighted ideas. And what I'd like to highlight here is that not only does it sort of smoothly implement the kind of mixture of expert style diffusion architecture in the diff, but it also changes the return signature of the forward function. So recalling the idea, the AI scientist proposed to do things like track statistics for visualization. The AI scientist smoothly changes the return signature to also track interesting summary statistics, and also can save these and handle these later on.
After writing the code and collecting the results, the model has to then produce a paper. This is kind of the structure for how we get it to write in proper LaTeX. So one insight from the project is that we use the same tools for code editing for file editing. And this allows it to then write in section by section the parts of the paper. So for example, it'll start with the abstract, then the introduction, then the related work and the background and so on and so forth. And the way we structure this is by kind of, for every section, we give a bunch of tips. And actually my advisor, Jacob Forster, a few years ago wrote this kind of guide on how to write a machine learning paper full of these tips. And so what we did was we just kind of took those tips and put them into the prompt for every single section. Basically, as we kind of then take the plots and put it into the results and write through the whole manuscript, we end up with this something that looks like a paper at the very end of this process of iteratively writing each section. One important bit is that we use Semantic Scholar to query for related works, and then use the results from Semantic Scholar to then put those citations into the paper. Obviously, this is a really important part of paper writing, which is trying to understand what are the relevant works that people should read, what does this work build on, and kind of hopefully integrate the paper better into the existing literature. I think this type of automated process can use a lot of improvement, but this is kind of seen as a first stab towards some type of end-to-end system that's able to do this. At the end of this whole process, where we write every single section and then including the results and then integrating the citations, we end up with this paper that it produces. And so this is actually the paper from the idea that we were discussing before, which was that dual scale 2D diffusion, and it uses the code that Cong was showing before as well. And you can see here it produced was this 10 pages of a paper. This looks like something that could maybe be submitted to like a workshop or to as like a student paper. And you can kind of see that it just at a first glance, it looks reasonable. And if you look at every single result, there's actually code that produces it. This is kind of the big idea behind this whole process for producing the final result. There's a big question of like, okay, we can produce a ton of these types of papers, and as you can see, like if you look at it, it looks reasonable, but how do you actually know if it's any good at scale, right? You can go through each individual one, but that just takes a really long time, right? The thing will write papers faster than you can read them. And so we obviously need a way to determine whether or not the papers are even any good. And so one kind of big question for how to do this is, what if we can instead do automated reviewing? And so here we start with like just a really simple approach to automated reviewing, which is just we feed in the manuscript to another language model and just ask it to write a review and then give a score. And this kind of seems a bit crazy, but when you actually look at how well it does on real papers, it actually achieves performance similar to humans in terms of accuracy. So the way we kind of generate this table here, so to kind of go over this again, we feed in the paper to the language model and we ask it to write a review and output a score. And the big question is like, how well does this actually do? And so we can actually compare to humans because I believe a few years ago, one of the top machine learning conferences did a double-blind study where they assigned 2 sets of reviewers to every paper. And we can kind of use this result to compare the accuracy of our model to the accuracy of humans on the same set of papers. And so you can see here that compared to humans, our model gets like slightly subhuman in terms of accuracy, but achieves superhuman performance across a lot of other metrics like balanced accuracy or F1 score or things like that, or at least close to superhuman. Yeah, this automated reviewing process isn't perfect, but it is maybe good enough to give you like a loose signal for whether or not the paper is any good. And so, for example, here's the review it wrote for that paper that I just showed before. So it produced kind of a summary of the paper, which seems reasonable, and then it produces strengths and weaknesses and gives it a bunch of scores. And this is the standard reviewing template that is currently at these machine learning conferences. So for every paper as a reviewer, you're going to be assigned to write a summary just to make sure you actually read it. And then there's a strength section they have to write, weaknesses, and so on and so forth. One kind of funny thing is that it used to be that there was no such structure to reviews for these machine learning conferences. But I think because the review quality is getting so low, they enforce this type of structure to the reviews. So it's kind of like prompt engineering, but for human reviewers. And we apply this to the model itself, it actually gets, according to our results here, like reasonably strong accuracy. So you can see here that it would reject the paper that we just showed. In fact, for most of the papers that we generate, it'll reject it, but we'll talk about that in the future slides. But you can see here that it kind of goes into detail on the paper, which is true. It does lack theoretical justification, and the paper doesn't discuss the computational costs, so on and so forth. So it seems to generally adhere to like reasonable set of review feedback. And so we can actually even do some further analysis as to how accurate this model is. So we can see here that when given a set of papers, our model outputs a score of that correlates more with the average reviewer score than reviewers agree with each other. So this kind of means is that our model is perhaps agrees more with the average score than reviewers do, which is a bit surprising. And you can see also that we take a lot of steps to kind of just do some prompt engineering tricks to improve the accuracy of our model. So you kind of start with just the base GPT-4, only gets accuracy of 66%. We add in some prompt engineering tricks, which include reflection, ensembling, and few-shot learning. And we can boost the accuracy up to 70%. And this is kind of the results that we use for the paper. So kind of to repeat the result in the top left here, the very top corner is the correlation between two reviewers on the same paper, their score. And you can see that they get a correlation or R-score of about 0.14. And this plot here on the top middle is showing the score of the LLM reviewer with the average actual reviewer score. You can see you get an R-score of 0.18. So the correlation between our score and the actual score is higher than the correlation between two reviewers for the same paper. So this kind of suggests that at least this reviewer, automated reviewer, seems somewhat reasonable. Given that we now have the system for automatically producing papers, and we have a reasonable system for automatically reviewing them, we can now start to launch large-scale experiments on trying to analyze the resulting papers. And to do this, we chose 3 distinct subfields of machine learning to explore with the AI scientist. This is 2D diffusion, nanogpt, and grokking. So 2D diffusion is what you saw here, which is all of the recent progress in generative images are usually a result of diffusion modeling. NanoGPT is like a small code base for language modeling, which is obviously like fundamental for GPT-4 and ChatGPT and these things that we see today. And grokking is a phenomenon in deep learning where neural networks will suddenly learn the underlying patterns behind data after a long time of training without any real like signal in between or before that. And so I'm going to pass it on to Rob, who will kind of discuss the result of the large-scale experiments that we ran on each of these 3 topics.
Awesome. Then let me take over. So basically, as Chris and Cong already introduced, we now have a pipeline of different steps to generate papers and to assess their quality afterwards. And we have these 3 code templates or experiment templates, which we use to then sort of generate new ideas and write papers. And what we're highlighting on this slide are basically 10 selected papers that were a result of this exercise, consisting of the diffusion, the nanogpt, and the grokking experiments. And as you can see, just by sort of glancing over the titles, they all sort of look into various different types of regularization or trying out new ideas in the context of these templates. And on the right here, we show like the reviewer score. And again, as Chris already highlighted, these papers would probably not be accepted at a conference at this point, but they are already at a high to medium quality. Again, to reinforce what Cong said in the beginning, we believe that this is sort of the GPT-1 moment of generative AI for scientific discovery. What we also did is we looked more closely at how different frontier foundation models sort of compare on this task of generating papers end to end. And what you can see here is basically for 4 of these frontier models, including Sonnet 3.5, GPT-4o, DeepSeek, and Llama 3.1, the 405 billion version. And we generated basically for each template 50 papers roundabout, and then looked at how the AI reviewer essentially scores these. As you can see, Sonnet and GPT-4o kind of consistently perform fairly well, while Llama 3.1 is not able to generate good papers. And surprisingly, like the open source alternative in DeepSeek Coder was actually also quite strong and was also very cheap in generating these papers. What we're kind of showing here is, to a certain degree, the robustness of the approach, on the one hand, to the type of frontier model, but on the other hand, also for 50 different ideas. To give you a little bit more of the statistics on how many of these ideas actually resulted in a paper, we show you this table where, again, on the row level, we show you the different frontier models. For each one of those, we generated in total 51 different ideas and scored them as being novel or not. And as you can see, for most of the Sonnet ideas, for example, they were deemed to be novel. And then basically based on these novel ideas, we then ran the basically the experiment execution, right? So the editing with the aider and then collecting the results. Again, there, like not all of the ideas sort of succeeded, And then again, afterwards, when writing the paper, also not all of them succeeded. But like at least for Sonnet, we can see that 38 out of the original 51 ideas were novel, passed the experiments, and also passed the write-up stage. Some of the things that I personally found exciting about sort of the results are shown here on this slide. So I can tell you there's basically nothing more magical than opening up one of these compiled LaTeX PDF files, looking at them and seeing sort of a plot or like something that you haven't seen before, right? So this is quite the cool moment, and sort of was one of the highlights of this project. And what we're showing here on the slide are basically two examples. One sort of being various plots that were generated by the AI scientist, which we didn't provide in the template, for example. And here for the paper that we used sort of throughout this presentation, you can see there are different visualizations of sort of weighting sort of local versus global timescale in sort of this dual scale diffusion approach. And down here, you can see like a novel plot where the samples are basically visualized by the gating probabilities, right? So this is something we didn't hard code, but sort of popped out ultimately by the AI scientist experimentation. And on the right, I'm showing you sort of one of my favorite ideas. So once upon a time in my PhD, I worked sort of on sparsity and this lottery ticket hypothesis and how to connect sort of sparsity with learning dynamics. And for the grokking template, the AI scientist came up with this idea of sort of looking at how pruning and iterative magnitude pruning sort of relates to this phenomenon of grokking and sudden generalization. Maybe to highlight here, like everything we've done is open source available. You can look at the code, you can run the code, but you can also inspect all the different papers and ideas and their execution, basically. So I would recommend checking out this link on the bottom, sakana.ai/AI-scientist, to get to our blog post and to look into all the material that sort of was generated as artifacts out of this project. To the final part of this, sort of the technical limitations, right? So one of them is pretty obvious, like the automated reviewer right now is basically not using any vision capabilities. And oftentimes for assessing a paper, it's not enough to just look at the plot, but also to look at, and not only to look at the text, but also to look at the plots. Another one is basically related to hallucinations and sort of the problem of verifying the results. We do have all the code available, and this basically can be run by any sort of person and be used to verify it, but it would be nice to have an automated way of doing so. Next up is we used fairly limited compute with the experimentation. So basically all the paper generations were completed within, let's say, 3 to 5 hours, but it would be exciting to look at longer runs and what the AI scientists can do with much more resources. An open question is how we want to communicate the results from the AI scientist, right? So in our approach, we used basically the paper format, but going forward, there might be other metrics to essentially estimate the impact of a scientific contribution. So what we want to do going forward is sort of do a bunch of direct improvements to the AI scientist pipeline, including sort of doing better prompt tuning, using larger templates, using more compute, and sort of potentially having an explicit archive of ideas and sort of generating better ones by sort of trying to do crossover between ideas, for example.